Hi, so this is your second lesson in mechanics, and if we look at the specification, we're going to have to understand, use, and derive the formulae for constant acceleration for motion in a straight line. So a couple of key words there: constant acceleration. We'll look at variable acceleration another time, but this is for constant acceleration, which is a little bit simpler. And motion in a straight line, again, we're not changing directions or accelerating into a circle, looking at any things like that. So it's starting off fairly basic. So then on the notes on the right, it says that learners should be able to recall. So that's bolded because these formulas are not given to you in the formula booklet. They are expected for you to be able to remember them. Okay, it seems like a lot of stuff to remember now, but you'll be so practiced at using them soon that they'll be second nature to you. So let's not worry about that. But as well as those formulas, you've got to be able to derive them. That means come up with them or explain them or justify them from substitution, interpreting graphs, or calculus. So calculus is differentiation integration. Again, all that sounds pretty complicated, but I'm going to go over that now, and it's really not as complicated as it looks. Then underneath, it's talking about gravity, but we're not going to be looking at that today, so we'll leave that there. And let's have a look at the first formula in derivation. So what does acceleration mean? So acceleration is the rate of change of velocity per unit of time. So how much your speed is increasing or decreasing per unit time, so per second. So meters, if your speed is in meters per second, or your velocity, sorry, then how much that's changing, meters per second, or meters per second squared. So if we look at a distance time graph, then we've got a few key points on here. So U is your initial velocity, V is your final velocity, T is time, so here's your velocity time graph, and you can see here by a straight line that is constant acceleration. If it was curved, it would not be constant acceleration, it would be changing at a different rate. You can see here, because it's constant acceleration, if you go over half the graph, it's gone up a certain amount, and if you go over the other half of the graph, it's gone up the same amount. It's constant acceleration. So like I said, U is initial velocity, V is final velocity, T is time, and A is acceleration. And the reason these letters are used, I should explain. So V is for velocity, obviously, and then somebody decided they wanted to differentiate between initial and final velocity. So initial velocity happens before, so we went one letter back in the alphabet. And then T for time, A for acceleration. That's fairly straightforward. And if we think about it, acceleration, if we wanted to find the acceleration in this graph, it would be the gradient of this line. So how do you find the gradient of a line? It's change in y over change in x. So if we realize that the change in y, so the difference between the initial velocity and the final velocity is just v take away u, there's the change in y. The change in x is just t. So acceleration, change in y over change in x. We have got a formula connecting acceleration, velocity, initial velocity, and time. And if we rearrange it so that v is the subject, we have derived our first equation. So final velocity is equal to initial velocity plus acceleration times time. If you think about that logically for a second, it just makes sense. So you start off at whatever speed, and then if you're accelerating at 10 meters per second, so each second you go on, your speed is increasing by 10. So 10 times 3 or 10 times 2 or whatever that is, that'll work out your final velocity. Okay, so keeping with the same graph, if we think about displacement, which is the vector quantity of distance, so S for displacement, D is for distance, which is the scalar quantity, so we needed to use a different letter, so they've used S because there's S in the word displacement. So if you want to find the distance traveled in a speed time graph or the displacement from a velocity time graph. It's the area underneath the graph. So if we do that in terms of u, v, t, and all that, we will generate another equation. So the bottom rectangle is u high and t wide, so it's u times t. And this is a triangle, so it's half base times height. So the half, that's divided by 2. Base is t, and height is v minus u. So that's that. So it looks a bit complicated. If we think back to our previous equation, v equals u plus at, and we substitute, instead of this v, we put in u plus at, we'll get this. Now, it seems like a big sort of jump. I'd advise that you have a go at working it out on paper, but it's simple enough when you think v equals u plus at. The u minus the u, they cancel out straight away. So all that's left inside this bracket is at. Expand the bracket, you get at squared, and it's a half. Okay, so it's a second formula. So if we think about it, we have got two formulas. This first one contains 4 letters, and it doesn't contain the 5th letter, s, for displacement. This one contains 4 letters and no v for final velocity. So we should be able to generate 3 other equations which use 4 out of the 5 things and don't use the 5th one. So that gives us flexibility when we're looking for certain pieces of information, and we have certain pieces of information. It gives us flexibility in what formulas we can use. So what you want to do now is have a go at deriving these equations from the ones we already know. So it said on the specification, interpretation of graphs, we've done that for the first 2, substitution for the next ones. So you're going to be able to derive all of these by substitution. If you want to have a go with no hints, pause the video now. And if you want to have a go with a couple of hints, I'll have a look at, I'll tell you those now. And then I'll go through what the formulas are and roughly how to do them. Okay, but I would advise you either pause the video now or in a minute after I've given the hints. So first hint is for this one, no acceleration. What you're going to do is you're going to take this formula, the second formula, and instead of a, you're going to put in v minus u over t. So if you can see this top one rearranged, you can get a equals v minus u over t. That's what we had initially. If you substitute that in there and simplify it, you'll get this formula. This one here, if you square this top equation, remembering you're not going to just square it term by term by term, this will go in brackets and be all squared. Expand the brackets, make a substitution from the second equation, you will get this one. And this last one, you're going to just make a substitution, so no initial velocity. You're going to rearrange this top one, so you get u equals v minus at, substitute it in here, and then you'll get your last equation. So if you want to have a go from those hints, pause it now, otherwise I'll go through the answers. So, like I said, this one here was a case of up the top here, instead of using this acceleration, you're going to substitute in v minus u over t, and it simplifies down to this and factorizes, because you can have minus a half of something plus a half of something. You've got this takeaway. It all simplifies down to this. Okay, if you can't get any of these, by the way, then just email me or ask me in the chat, and I'll talk you through it in a few extra steps, but hopefully you can. This next one, like I said, if you square this top equation, then you're going to get u squared plus 2uat plus a squared t squared. Now then, if you think you've got u squared at the start, so that's fine. The remaining terms, if you factorize out 2a, then what you'll end up with is exactly this, and then that is equal to s, so you can substitute in. That's probably the hardest one. And this last one, if you substitute in, so from this top equation, u is equal to v minus at. If if you substitute in v minus at for this u, it'll simplify down to this. So what we've got is we've got 5 equations. There are only 4 in specification. This last one's not actually in there, but for the sake of completeness, I thought I'd let you know, because it does have its uses. But once you've got a few of these equations, anything is possible to work out, because sometimes you just have to work out something else first. But it's obviously much easier if you can go directly to an equation. So we've got 5 equations. Each contain 4 of the 5 different things, so they each have a different use. Okay, collectively they're known as SUVAT equations. It's a rearrangement of these letters, just in a position. They've rearranged them so that it's pronounceable, and it's just the equation of motion equations, and it's for constant acceleration. So that's the derivation of the formulas. Now let's have a look at using them. So a cyclist is traveling along a straight road. She accelerates at a constant rate from a velocity of 4 meters per second to a velocity of 7.5 meters per second in 40 seconds, and we want to find the distance she travels and acceleration. What's always useful in these situations is draw a diagram and write out the letters SUVAT and put in numbers where you know them and question marks where you don't know them. And that will help you determine what you know, what the diagram looks like, so what's actually happening, and which formula to use. Once you've done that first step, it's really quite straightforward. It's just put some numbers in, get an answer out. So this is the diagram you should get. And so she accelerates. She's going from a velocity of 4 meters per second. So there is the original velocity, 4 meters per second. Accelerating, so going this way, up to 7.5 meters per second. There's a distance between them. We know u, we know v, we know t. We don't know s and a. So it says model the cyclist as a particle. Don't spend a lot of time drawing out a bike. It might make the diagram more realistic, but it's not really going to help, and it's just going to take it more time. So like I said, put in what units you know, what you don't know. It's also important to just double check all the units work. So it's best to work in SI units. Most things will be in SI units. So meters per second, seconds, distance will be in meters, acceleration will be in meters per second squared. It's all SI units. So once we've got the diagram, we can have a look, right? So we want the distance traveled. So we know u, we know v, we know t, and we want to know s. So that means we've got to use this equation here. Okay, so if we use this equation here, we can put in u and v and t, and we just get out the answer, s. And because we were careful with the units before, our units are straightforward now, and it's just 230 meters. The second one, we are looking for v. Now, because at this point we know 4 of the 5 things, we could use absolutely any equation. Okay, so you can use any equation, but this is a pretty simple one. It doesn't involve halves, it doesn't involve squares, it doesn't involve brackets, so it's probably the best one to use, but you could use a number of other ones. Put in the numbers we know, so we know the 7.5, the 4, and the 40, and we get out our answer of 0.0875. So it seems like a small number. You might think that you're wrong, but in reality, accelerations are quite small. If you accelerate very quickly, then it's like being on a roller coaster. It's not that pleasant and it's not that healthy. Another thing to consider when you're picking which equation to use for part B. Now we worked out that distance s being 230. If we worked it out wrong and we used it in part B, we'd make another mistake. So it's often best to ignore what values you've already worked out and see if you can work it out from what's given in the question, because you know they're right. But sometimes that's not an option. Sometimes you have to use what you've used previously, and in those situations you get error carried forward marks. Okay, remember to use units, and that's how you do this sort of question. Let's look at another example. So we've got a particle. So it doesn't always say a cyclist. It'll sometimes just say a particle, which is just a basic point. And moves in a straight line from A to B, constant deceleration, so that's negative acceleration. At A, it's 8 meters per second velocity is, and at B, it's 2 meters per second. Find the time taken to move from A to B, and the distance from A to B. And then we've got some more information, but we'll deal with that later. We'll look at the first bit first. So, first step, draw a diagram. So, it's always important to label which is the positive direction, especially when you are dealing with decelerations and negative numbers and things like that, because you never know when something's going to be going the other direction, and mistakes can happen if you're not clear with what direction things are going in. So you've got it going from A to B, it's slowing down. You've got 8 for your initial velocity, 2 for your final velocity. Your acceleration is negative, so minus 1.5. And we're asked, we don't know what t is and we don't know what s is. So it's asking us for the time taken, and then it's asking us for the distance. So if we look at what we know and look at the formulas, you'll have to look back at the formulas a lot to begin with, but as time goes on, you'll start to remember them. So v equals u plus at is the best formula to use. And you put in the numbers you know, so 2, 8, minus 1.5, and t, and it'll tell you 4, so 4 seconds, because we were working in SI units. And the next thing we're looking for is s. And again, given the information we know, it's probably best to use this formula here. There are other ones available, but this one does not involve squares and halves and things like that. And if you put in the u, the v, and the t we just worked out, then you get an answer of 20 and 20 meters. Okay, so then the next part of the question was asking for velocity from to C and the distance from A to C. So it continues with deceleration, and point C is 6 seconds after that. So we know that t now is 6 seconds from A. We know the initial velocity. We know the acceleration. This is a typo. This should say minus 1.5. And we don't know the final velocity. That's what it's asking us. So if we put in the v plus u, v equals u plus at, put in the numbers, being careful to put in the minus, and you get an answer of minus 1. So you might think you've done it wrong, but velocity has direction, which means it's slowed down, it's stopped, and now it's moving in the other direction. So that's why direction was so important in this, labeling the positive direction. So some mark schemes will be more fussy than others. Sometimes if you leave an answer of minus 1 meters per second, that'll be fine. But sometimes it's best to just be really clear and say that it's 1 meter per second in the opposite direction. This means the direction B to A. Okay. You can say all these things which are put down as little symbols notation. If you say them in words, that's perfectly fine as well. So if you said the velocity is 1 meter per second in the direction B from B to A, that will work just as well. Then it's asking us for the distance from A to C. So if we use the other formula, we've got different numbers to put in. So u, 8, v minus 1, we just worked it out, divided by 2 times by 6, you get 21 meters. Okay, if you put in 1 there, because it's going 1 meters per second, you'll get a very different answer, and it would be wrong. Okay, so you've got to be careful. And you'll also notice that all these examples seem to be using just these 2 equations, and that's not just a coincidence. We're going to go sort of slowly through this. We've derived all those equations. It's worth you going over those derivations and checking you could do them, because it is in the specification that you might be asked it. But as far as practicing using them, we'll just practice them a couple at a time, and then in a later week we'll practice the other ones, and then we'll move on to vertical gravity, variable acceleration, all the different things. We're just building up slowly. Okay, so let's have a look at last example before we have a go at an exercise. So, car moves from traffic lights along a straight road with constant acceleration. The car starts from rest. Traffic lights. 30 seconds later, it passes a speed trap where it's registered as traveling at 45 kilometers per hour. So we'll find the acceleration and distance between the speed trap and the traffic lights. Okay, so a couple of things. This 45 kilometers per hour is not SI units. This hour does not match with the seconds, so that's a problem. Also, if you look at it, you look and you think that you've only been given 2 numbers when all the previous examples you've been given 3. The third number is the car starts from rest, the car starts from 0. Okay, so first thing we're going to do is convert the units. So 45 kilometers per hour. We went over this in the previous lesson, how to do this. So change the kilometers into meters times by 1,000. Change the hours into minutes and then seconds, divided by 3,600, so it's 12.5 meters per second. Then a little diagram starting at 0, going to 12.5. We've got the time. We don't know the acceleration, we don't know the distance, and they're the 2 different things we are asked to calculate. So looking at what we've got and what we've got to work out, we should use v equals u plus at for the first one. So put in the numbers we know, and you get 5/12. Now, if you change 5/12 to a decimal, it will give you some long decimal. So putting 5/12 is exact. Okay, the exact answer is usually best, but if you are going to put something as a decimal, then you should round to 3 significant figures. And if you use this number in a later calculation, use the exact version, because if you round it and then you use a rounded value later on, it will cause errors, just rounding errors as you go along. So the next thing is asking the distance between them. So if we look at the other formula we're practicing at this point, so put in the numbers. We know a u is 0, we know that v is 12.5, we know that t is 30, so 187.5 meters. And that's how to use these couple of equations. So just to recap what we've had a look at today, we've looked at the derivation of all the SUVAT equations, the specification, and practicing 2 of them. And now I want you to have a go at an exercise practicing 2 of them. It's exercise 9C. It'll be attached, and have a go at that. Some of them are very straightforward questions like what we've just looked at. Some of them will get a bit more complicated. They might throw an X or 2 in there, so don't think that it's all going to be easy. Don't just do the first couple and think that that's, you can do the first couple so you can do the whole thing. It will get a bit trickier, so work your way through it, and remember to ask for help if you